Hello, this is Deborah Barrett with the Cincinnati State Physics Department reviewing the mass-weight relationship for objects close to the Earth's surface. For objects close to Earth, the weight is equal to the mass times the acceleration due to gravity. Since weight is the short name for the force of the Earth's gravity acting on an object, the weight is often represented as force subscript g, where the g is usually written lowercase. So our formula is weight equals mass times acceleration due to gravity, or force of gravity equals the mass times the acceleration due to gravity. This chart shows the different units and values that we use when we're doing mass weight calculations. Generally, we want to work within one row of the chart. So for example, if we were doing SI calculations, we'd stay in the big metric row of the chart. Or if we were doing small metric calculations, we'd stay in the CGS row of the chart. So let's actually look at a sample calculation. Finding the weight of a 6 kilogram chair. The first question to ask yourself is, have you already been given the answer to the question? Is 6 kilograms the weight of the chair? In the chart, we see that 6 kilograms appears in the column for the mass units, and that tells us that 6 kilograms is not the chair's weight, it's the mass. So we will need to do a calculation, and for that calculation, we use our mass weight formula, W equals mg. In this formula, we are going to be filling in the mass of 6 kilograms, and multiplying that by the weight, or the acceleration due to gravity. Now, since the kilograms is a big metric unit, we're going to want the big metric version of acceleration due to gravity. So we're going to use 9.8 meters per second squared for that acceleration due to gravity unit. When you're doing a calculation that has a fractional unit, it's a good idea to write the unit vertically to avoid any mix-ups in the way you're handling the units. So I'm going to make this meter per second squared written vertically. Then we're ready for the button punching, in which we have 6 times 9.8, giving us 58.8. And then for our unit, we have kilogram times meter, and the second squared is still in the denominator. So our unit looks like this. This unit is equal to the definition of a Newton. We have a kilogram meter per second squared here. In the chart, we see kilogram meter per second squared is a Newton. So we can rewrite that 58.8 kilogram meters per second squared as 58.8 newtons. And then if we want to keep in mind the sig figs, since we started with just one sig fig, we would round officially to just one sig fig, in which case we would say 60 newtons, or to be really precise and clear, 6 times 10 to the first newtons. That way someone can tell for certain that we are not just giving a rounded off number there. So this would be the surest answer to the problem. Now, let's do a second sample. Let's take away the 6 kilogram chair and find the mass of a 125 pound woman. The first question, once again, is have we already been given the answer to the question? We have a 125 pound woman. Is that her mass? In the chart, we see that pounds are a unit of weight, and so we know that we have not been given the woman's mass, we've been given her weight. So we do need our formula, which is that W equals mg. Since this time we're going to be trying to find the mass, a good idea would be to solve the equation algebraically for the mass before we bother filling in any information. So let's divide both sides of the equation by g. And that will give us a formula for the mass. So we'll have mass equals W divided by G. And I'll just put the little... So now we have mass equals weight divided by acceleration due to gravity. Now we're going to fill that in. Mass equals the weight, which was 125 pounds, and that's going to be divided by the acceleration due to gravity, which, since we're working with the English system, we want to look at the English row of the chart and take the acceleration due to gravity of 32 feet per second squared. So 32 feet per second squared. And like we mentioned before, when we are doing problem solving, if we have a fractional unit, it's better to write that fractional unit vertically. So I'm going to put the second squared in the bottom of the foot per second squared rather than writing it horizontally. Now, it's easy enough to do the calculation for the numbers. We have, looks like I came down too far. We have 125 divided by 32, which is 3.9. And then in order to find out the unit, a good plan is to take the pound and break it down into the units that define the pound, a slug foot per second squared. So for this pound, I am going to substitute in a slug foot per second squared. I'm going to bold this broken down unit that is equivalent to the slug, so that we can kind of keep, or that is equivalent to the pound, so that we can kind of keep track of how this unit came about, that we've got our slug foot per second squared, which originated as the pound. So the slug foot per second squared bolded here is equivalent to the pound, which is bolded here. Now that's supposed to be divided by this foot per second squared. So what we're going to do is show that being divided by the foot per second squared. And I'm just going to try copying it down. And that worked pretty well. So the unit we had above of pound divided by foot per second squared is equivalent to the slug foot per second squared divided by foot per second squared. When you write it this way, you can probably see that the foot per second squared here is going to cancel with the foot per second squared here, leaving us with just a unit of pound. And so we see that our answer in the end is going to be 3.9 slugs, which is good because a slug is an appropriate unit for mass in the English system. That completes our review of the mass-weight relationship. Thank you for joining me to review mass and weight.